So, hello, I'm Nick. I work at Force. I do bring up prototypes, usually RISC-V prototypes, and I'm going to walk you through a part of the process, like how this is done. So I'm doing the system software side, but before I get my hands on actual hardware, the hardware guys are working are already doing part of the job. Like they create the designs, they create unit tests for them. They both pre and post synthesis. They're running tests on simulators. They're running tests after with co-simulation when they run their stuff in the FPGAs. But it's a complex process, and the more complicated the hardware is, the more complicated the tests become. But those kind of tests are very slow. They are there for basic stuff, because especially those that run under a simulator before you do the synthesis. So you cannot expand the test coverage. You can only test for specific things and do very basic stuff there, or else it takes a lot of time for the test to work. And you want those tests, by the way, to also, you want them to be part of your CI flow. So when you compile the hardware, let's say when you do you create the initial before you create the bit streams, when you run them through very later, you want those simple tests to be part of your CI flow, so they can catch bugs early on. So the more when we move on, like when the process moves on, we need to create more complicated tests, because and those tests cannot be run under these circumstances. So we need to, when we do have the design on the FPGA, we need to start working on more complicated tests that not only test the core, they test the interoperability between the various IPs in the SoC. You get to see memory subsystem tests like cache coherency, which is a big thing, quite hard to test in any other setting. So security related tests, when you do need to provide for validation for the random number generator you have there, or you need to do to make sure that your memory protection mechanisms are working properly. So you need to do transactions, do stuff that you cannot easily do on a per IP case, like when the previous set of tests work. And even after that, even after we have the basic tests during the CI flow from the hardware team that are mainly there for validation, even after we do the very basic tests during early bring up, when we do have everything integrated in the SoC, in the design, and we start running some small things there, some small bare metal tests. Even after the whole process, when the chip is finally out, things can go wrong. Okay, things can go wrong in every stage, because not. So, for example, even if we manage to run all those tests and we expand the test coverage and we manage to boot Linux on the design before we send it for tape out, after the tape out, we can have more things going wrong, okay? Because now it's not part of it's not in an FPGA anymore, it's an ASIC. You get things, you may have bugs in the process, you may have bugs in the PCB. So you need to also have tests to figure out, to debug things after the tape out. And in many cases, those tests are running in a very constrained environment. For example, we've been through one of the common things that can go wrong is DRAM, okay, where you have your chip ready, and suddenly you don't have any memory to play with. So before you go back to the drawing, before you say that this thing is we cannot do anything about it, you still need to test whatever possible. I mean, any other peripheral, whatever test you can do to at least make sure that what parts of the system are working properly before you may find other bugs as well. It takes a lot of effort to to do this, and you need to run very, very targeted tests that are very small, that can run in a very constrained environment. And this allows you also to run them very early, and also allows you to run them when the full, let's say, when the system didn't work as expected after the tape-out happened. So we have a small framework for running those bare metal tests. It's basically a simple environment. There's no operating system. There are some libc functions. These are very small tools. We don't do any, it's not meant to be generic. It doesn't have any device tree parsing, so we have to hard code the addresses of the peripherals of the base memory or some parameters. You can see an example on the screenshot there. For example, in order for the get clock to work, we need to tell the software how many cycles the CPU does per second. So these tests need to be like very small, to the order of a few kilobytes. Because, for example, when you don't have DRAM and you may have some SRAM, you may not even have SRAM. There is a chance that all you have is your level 2 cache that you can use as a scratch memory. So you don't have, those tests need to be very, very efficiently written. So we have this very simple, let's say, framework that we also use not only to write tests for bring up, we also use it for educational purposes because it's very simple and quite. And after we are done with those bare metal, we keep enhancing this. Here are a few examples of such tests. So, for example, you can see a very simple UART test in the middle of the screen. That's like a hello world to make sure the console is working properly without interrupts. If you want to test interrupts, you'll go to the interactivity test, which is on the left side. And this is the simple version of the interactivity test. You basically just do input output there and you see how the core interacts. This uses interrupts for the UART. And there is also a multiplayer version of this that also uses interprocessor interrupts, and it also uses timer interrupts. So we have a simple test that tests the core, the PLIC, and the CLINT to also test. So you test for external interrupts, timer interrupts, IPI interrupts, and see that everything is working properly with a very, very simple code there. If anything is wrong there, when you try to run Linux or when you try to run something more complicated, it will be pretty hard to debug. So you better catch these kind of bugs early on with such simple tests. We have a core Mac. We have a bunch of benchmarks. You see here SA3 or SPMV. And you also see when we go to more complicated hardware, for example, you can see on the right, we are testing for networking. We have a small test that enables test an IMAC light in this case, and it connects to the network and fetches the next boot stage. But there is a lot of where we are improving this. So we want to add more to our collection of tests. And after all this, if all this works and you get your the validation passes and the bare metal test passes, they pass. By the way, there is also a set of tools from RISC-V International for making sure that your core is compliant, the architecture compliance test. When everything works fine, it's time to start working on Linux. But booting Linux is a complicated process. So here is a generic way, a generic approach. So your boot ROM will start, it will fetch the device tree image, or it will already have the device tree image included. It will fetch the first stage bootloader from somewhere, usually an SPI flash, for example. Initialize it. The FSBL, the first stage bootloader, will then fetch the firmware image from somewhere, probably also some kind of flash. And the second stage bootloader of the OS, probably from storage or network. Then you have your second stage bootloader, which may be there, like U-boot or Grub or Tianocore or whatever. And then that if such a second stage bootloader exists, it will also fetch the operating system image, mostly from storage or network. You have more support there for more file systems. The more you advanced in the boot chain, the more complex the software becomes. And finally, you have the kernel. And now the kernel also needs to fetch the rootfs from somewhere, usually from storage, in our case from network most of the times, because we don't have storage in the FPGA, in our FPGA prototype, so we do a lot of stuff with NFS there. This is a complex process, and if you are doing debugging, you don't want a complex process. You want the process to be as simple as possible so that you don't have a lot of noise there. So to reduce the process, we first use the first stage, the firmware as a first stage bootloader. So these two things are combined. Uh, and OpenSBI, which is the reference implementation for the firmware that implements the supervisor binary interface on RISC-V, also can be used as a first stage bootloader. This is very convenient. We don't use a second stage bootloader, no U-boot, no grab, nothing like that, because we can boot the kernel directly. This also, the cool thing with OpenSBI is that you can use the kernel as a payload to the binary. So you can link basically the kernel binary inside the binary of the first stage bootloader, which is also the firmware. And then you can also, so you get rid of this thing as well. You don't have to fetch any other images. And then finally, we can also have a small initramfs with basic tools that we can also embed in the kernel binary. So we can embed we have a small rootfs that we embed in the kernel image, and then we embed the kernel image in the OpenSBI binary, and we have one binary with everything we need in there. So basically, it's one payload. We put it in memory, jump there, and things happen. We don't have to do multiple fetches of multiple images. So this is how it looks like. It's much simpler, much easier to debug. However, even if we've simplified the boot process, but the kernel is still a big thing, right? It's a complicated piece of software. And if we start by running a full-blown Linux distro like this, and there are bugs that are earlier on, it will be very hard to debug. It will have a lot of noise. So we start with a simple setup with no networking, no storage. We just have like a small, this is in terms of kernel, we don't have an MMU. MMU is, by the way, a very common source of hardware bugs. So we've seen this in the past with, we're using, developing cores, or we used cores from for Ariane, for example. When we used Ariane for the first time, when it was, now it's CVA6, we found bugs there. Okay, things didn't work as expected. And finding those bugs, it's not easy. When you first do, you can do bare metal tests for testing the MMU. But when Linux boots and starts doing context switching and start doing fences, and you start doing more complicated things, things break. So you could start using, initially we start using Linux without the MMU disabled. This also implies a special rootfs compiled in a different way. We don't have networking or storage, obviously. We don't have many drivers to get in our way, or frameworks. We have a very small kernel. And then when this works and our tests pass there, we start expanding the test coverage. We enable storage and networking. And then we allow multiple users. We can mount an NFS share, for example, at this stage. And finally, we go for a more full-blown kernel configuration that allows for a full Linux distro to work. That means we enable more frameworks in the kernel. We enable more functionality of the normal allocators, the networking subsystems, the net filter, lots of frameworks, a bunch of things that will be enabled in a Linux distribution, in a full-blown Linux distribution. BPF, it is enabled. And basically everything you need to run systemd, to run all the tools that you'll get in Ubuntu, for example. So this is the last step, okay, after everything else has worked. And if you worry how to install, because right now, if you try to get a rootfs for Ubuntu, for example, you won't find a tarball out there. There is a tarball in the cloud in some of the cloud image servers from Canonical. LXC servers don't have Ubuntu. And Alpine, I get you need to if you get a mini rootfs from Alpine, it's very basically empty. You don't get an init system because it's designed for containers. And Alpine is very good for us. Our next slide. So when we go to user space, initially in our very simple setup, we only have BusyBox. And once we add networking, we add SSH and IPERF there and a bunch of other tools. Then the next step is to go to Alpine. Alpine is a small Linux distro based around BusyBox. So basically it's the same BusyBox we are using, because we also compile this using the Muscle library. Muscle is an alternative to glibc as a C library used for Alpine. And one of the cool things with Muscle is it creates small binaries, which is what we want for this constrained environment. And then like the early stages of testing. So before we go to Ubuntu, we use the Ubuntu file system, the Ubuntu rootfs. We use Alpine, which a small rootfs in Alpine. It could be like 10 or like 15 megabytes. You can fit it in RAM if you want. So we can do a small installation even if we don't have storage and we want more tools to, for example, test some extra hardware or perform some further testing there, download stuff. I don't know. Setting Alpine inside the initramfs, it's quite simple and fast. And it's basically the same stuff we have. It's also built around BusyBox. It just adds more extras, and it's simpler than including it in the original build script. So then we move to Ubuntu. For Alpine, for example, since we get the rootfs out of the box, we need to build it out ourselves. And same goes for Ubuntu. For Ubuntu, you can get a rootfs out of the box, but it's a bit complex. It has too much stuff. So we have a bunch of installer scripts. So I have the link here for YART. YART stands for yet another RISC-V tool. It's a set of scripts we use for bootstrapping this thing, for building the kernels and rootfs. So this tool can build an Alpine rootfs for you and an Ubuntu rootfs for you. So you don't have to do the bootstrap or stuff. So why no-MMU? I mentioned earlier that MMU is a common source of hardware bugs. And it makes sense to, before we go to full-blown Linux, when it comes to the kernel, to begin with something simple that doesn't have virtual memory. So you may ask, why don't you just go for a free RTOS? The case for a simple RTOS before you go to Linux, why you prefer using Linux in no-MMU mode? One of the main things here is that most real-time OSs, they run on M mode. They don't run on S mode. And in our setup, because we want to move to test the more privileged modes and move to a more representative setup after the bare metal tests, and more setup that will approximate the normal Linux setup. We prefer using something that also utilizes S mode. Or even in the future, when we do have the hypervisor extension, we may want to also utilize H mode, like HS mode and VS mode. We don't have tests for hypervisor yet. It makes it easier for us to have a more representative scenario. It also makes it easier for us to compare the behavior between no-MMU scenario and an MMU scenario. So when we enable the MMU on Linux and we use another more capable rootfs, we run the same code basically, and we can compare the behavior. We can find, for example, delays there when it comes to no-MMU. We can see what's the impact of context switching. We can see the impact of fences. We can see more stuff when we also debug hardware at the same time. Measurements the hardware team gets while we do this. Also another thing is that it's more easy to maintain. Actually, when you want to build an application for an RTOS, you have to go through an SDK usually. If you play with Zephyr or RTOS or FreeRTOS, you'll have it's a different build flow that you have to follow, which is more complicated if you think about it. Because if you just go with Linux, you have the same tool chains, the same tools for building the full-blown distro, and you can use the same tools for building something very small. So if you just put some FreeRTOS or Zephyr, I don't know, Yocto in between, you'll suddenly have a lot of dependencies there. You'll suddenly depend on an SDK or other stuff that will complicate the flow of building these images. So you get a few limitations on MMU Linux. You don't have fork. You don't have copy and write. You don't have memory protections. Okay, it's for testing. It makes sense, but your software will have some limitations. It's not you're not going to use exactly the same stuff you'll be using in the MMU scenario. You need to know about this so that you have an idea of the test coverage, like what things you'll be using. When you do mapping on files, things change. You get excessive fragmentation because you don't have virtual memory, of course, to your allocation. Your allocators are different. You don't have swap. or lazy binding or stuff like that. But for small tests, for running testing specific use cases there, or for example, for testing drivers, that's again something that makes sense. If you want to test, for example, the PCIe driver, okay, you can write a bare metal test for it. It will be very complicated. If you just run no-MMU Linux there and you use the already the already driver that's already in there, it's much simpler. And for you, it's way less work. But you still can do lots of stuff even with those limitations. The binaries, as I said, the tool chain is different too. It's not only that you have limitations on the system code side. The user space is also built differently. The binaries need to be position independent because now that you do not have virtual memory, you need to be able to place them everywhere, anywhere in the physical memory. That's why they need to be position independent. There are two approaches here. The flat binaries, that are let's say, the old way of doing things. And in our case, it's unusable because our memory is very high up and we cannot use the flat binaries. You don't get shared libraries, you don't get dynamic loading, no DLOpen or stuff. For that, there is a newer approach, which is the FDPIC, stands for file description function descriptors position dependent code. Basically, it allows for shared libraries. It allows for dynamic loading. And it is also a bit portable. You can use it with MMU enabled. So this is cool because we can use the same user space for testing both the MMU and the no-MMU scenarios. So in order to compile this, you need a different tool chain. The spec is not there yet for RISC-V. We have one tool chain that supports it based on UC-libc or micro-libc. Here you can see the difference in the binaries. If you see the one in the left, it's the normal one. You can see it's a statically linked busybox, the simple thing. And the type on the ELF says exec, it's an executable. This runs in the MMU case. The other two, the second one is busybox running on this no-MMU scenario. You may see that it says dynamically linked with an interpreter being the linker, the UC-libc. This allows for shared libraries because you go through this linker and the linker will put the library somewhere in the memory, and when another application needs it, use the same memory. That's why you get shared code, but the data would be per context, let's say. You see that it's position independent, the busybox, it says DIN, and same goes for the library, is a shared object file, which is static PI. So it's position independent, but statically compiled. So it's a shared object file. It's a bit of a complicated thing. It may seem complicated. It's not your standard toolchain, not your standard C library or your linker. But it works. And it's been working since, the original support for no-MMU Linux on the kernel side went in 5.5. I think it was added there to make the Kendrit SoC work. Kendrit has an MMU, but it's a non-compliant MMU. So it has S mode. But we couldn't use, you could have virtual memory, but it didn't follow the RISC-V spec, so we dropped it. And it's been there, but not many people used it. And at some point, at least that's what the community thought. And when the kernel maintainers said, okay, let's drop this, suddenly many users of this functionality came up and said, oh, no, we want this. We really need it. We use it. And the support became more mature. There are still some gaps there, but it gets better. And on the user space side, things are not evolving that well. Not that fast. We still have it's until with flat binaries do not work for us. Not many people are working on that because it's old school. It's the old approach. The PS API that we need to use to really have shared the libraries with the no-MMU scenario for the FDPIC is not there yet. There is some discussion going on. I don't know how it's evolving. I remember there was a large discussion on GitHub about this. From our part, we added support for having a toolchain, because also creating a toolchain is a bit of a challenge. If you try to use cross-tool-ng to create a UCLibc based toolchain, it's not there. It only was added very recently. I don't think it's still. Last time I saw it wasn't there. So we have a toolchain repo for RISC-V. You can see the link here. It's the let's say the official, it used to be the official, it still is the official repo for maintaining a set of toolchains. It includes GCC-based and LLVM-based toolchains for newlib, for glibc and muscle. And we also added there support for UCLibc. By the way, we also added muscle support there a couple of years ago. We also, recently there was another issue with the CI. We also fixed that. So we have some contributions on that tool, on that repo. And here you can see the whole thing running. On the left side, you see MMU. You notice the virtual addresses on the bottom, like 3FA, blah, blah. These are high virtual addresses. On the left side, you'll see that all of them are 800. They're all physical addresses. You'll also see in the kernel log that in the left side, at some point it says disable 4-level and 5-level paging. It means it uses paging. It uses 3-level paging. On the right side, there is no such thing because it doesn't use virtual memory. So what are our next steps? Well, always needed, more tests are needed. The more hardware we get, the more tests we need to write. For the guys mentioned hypervisor support. When we get hypervisor, we'll need to write a bunch of tests for it. It would be useful to open source our bare metal stuff, at least most of it, the things that are readable. Some of the no-MMU fixes, we found some bugs that are some changes that would be useful, and we'll need to upstream those. We keep in touch with upstream projects. We monitor them. We try to contribute from time to time. And another thing that would be useful was to go create an even more complicated flow. I mentioned earlier, I show you the simple flow here, the secret boot flow. It would be useful to add a second stage bootloader there to mimic a more server, something that looks more like a server or desktop. So it should use UEFI and ACPI, Tiano core, even though I hate ACPI. But anyway, this is what servers are using. So we need to have to put that in the mix as well. Or if you have any suggestions, we can talk about it if you think other things, some other stuff would be useful.